Okay, good day. My name is Normunds Jēkabsons. I am working from Latvia University and I am consulting sometimes about engineering and modeling. And today I am not involved anyhow in any modeling related to C or MarTe, yes, unfortunately. But therefore I will give more broader presentation. I will just talk about my experience with open sourced software for modeling in some kind of real world problem situations. Maybe it's used when Vladislav invited me. That was the only thing which I can propose. So how can I get to next slide? Okay. I would like to briefly summarize approximately 20 years experience, and I will show some systems which can be modeled. And that doesn't mean I am then you can, perhaps one can do much more with OpenFOAM, but it at least can give some inspiration. Maybe that's all. I am not aiming on something very large with that presentation. First, what is OpenFOAM? I'm sorry about about my boring fast slides. Later on will be more with pictures. But when as a beginning definition, I just put some text. And OpenFOAM, it's kind of, I would like by my words, it's a library written in C++ for numerical linear algebra and with some kind of tensor analysis elements, and around that library is some solvers which are built around like computer fluid dynamics solver, which works as volume method. Yes. Finite volume method solvers and also finite element method solvers exist, and all this package is first was commercial. Then since 2004 it went free and went open sourced, and it can be compiled on Linux, Unix, Windows, and this code is maintained by three companies, generally now three parties. One is CFD Ltd, which is holding trademark, or code is open, but trademark is not, which with property. Then CFD Direct Ltd, which I think more development is on their side right now. And another branch is one of the developers, Jekabsons, this branch which is called OpenFOAM Extended. I like it the best because, let's say, when they split, it kept some new model, very interesting advanced models like diesel engine with cylinder with piston and with ignition. Everything was else with very impressive mesh morphing, and also rotating coordinates. Rotating mesh was first introduced in that version, but nowadays any of those versions can be used. What is basic traits which maybe we have to know when we start to use that? Calculations are driven by files. We have some files in directory tree, and yes, normally no one uses graphics. Files can be modified. A solver is running. Solver is giving you some results, and if you modify those files, you can get solver react on that. And let's say if you say from that moment we will use another numerical schema for velocity discretization, then you can get next schema for velocity discretization. It will load next library, and it will work. It will continue to solve your problem. It has limited mesh generation force, block mesh, but those are really limited, and they are not really on so advanced as in commercial software. And for visualization, here is a ParaView tool, which is outside product, but also open sourced, is usually used. And generally, it can use unstructured mesh. They are one of the fast, I think they are fast, who used cells with arbitrary shapes. So you can use arbitrary polygons. Later on, it was incorporated in ANSYS software, for example. They took it from OpenFOAM as much as I know. They have multi-domain. Nowadays, they have multi-domain approach, and you can have different domains with different physics in domain. We can also use multiply fields and multiply physical systems in different parts of the model. Also, it's very good for parallel scale computing. It's very well parallelized. It's scaling good on lot of on systems with more cores, and you also in systems with more nodes. Yes, because the number of cores is limited. Here is also GPU solvers, and it's more important, of course, it's easy to modify code. When I started it was 2005, and it was I know some my friends, I know some group in Latvia University. We did some collaborations, and they worked on crystal growth research. And they did their work for crystal growth companies in Germany. Actually, for a certain time, I think 1/3 of they consulted those companies, and they did research for them. And they needed some kind of software to go forward for numerical simulations. And here it was decided that it will be open sourced, and we started with OpenFOAM at the time because it was first introduced. It was recently open sourced, and it was recently, and it's looked as best as on the moment what can be. And this particular example, and then I started. It was very limited at the time, and I wrote some additional libraries and code for that. Let's say for buoyancy, I think my implementation of buoyancy is fast, correct implementation, because OpenFOAM itself got correctly it in, I think, 4 years later. I can be proud of that. But yes, and the example itself is, which I'm demonstrating you, it is crystal growth example, and this by so-called floating zone model, where we have silicon beam, which is heated by electromagnetical inductor. Then it melts, and the melt is in that middle, yes, in this neck. This melt is just falling down, and here below is melted zone. And below this molten zone, crystal is starting to grow. It's growing, and this the device is pulling it down. And that was first model. I spent almost 1 year, and it was very successful. And this is actually because here is buoyancy, here is temperature, and so on. But it's in general, it's correctly described phenomenon. Next example where it was used it was here in Ventspils University. I worked for some time with in Ventspils University College, and our group attention, we did some we had some modeling group was focused on wind turbines at that time and we did some simulations related to vertical wind turbines, as you see on on the pictures. First, such a turbine was first. This possibility was to do that correctly was introduced in commercial software in 2002 in ANSYS, I would like to say fluent, but already in some 2006, I think it's even earlier. There was some division in Canadian people, guys who introduced it in this extended OpenFOAM version, which I mentioned. So everything was in place, and we started and we did some simulations. The main idea is that we have two mesh. One is staying still, another is rotating, and they are not non-conformal mesh. In this rotating mesh, we have turbine or propeller, whatever. Since this mesh is rotating, it's rotating with all solids inside, so therefore boundary conditions are simple. But between those meshes another boundary which is opened and closed at every time step. And so this was already stock solver in development version. Not stock, I don't know the software code, but anyway we compiled it and it worked. And we did treat on different blade configurations. And also there was some experimental checking of that, and finally we got pretty well fitted curves. So that was also one successful situation, and it can be also used. Such simulations can be used also in aviation, and can be used in some maritime things, because related to some kind of rotating machinery which is emerged in liquid or in liquid or air. Third is my example would be maybe related to more distant things. For years I was involved in some kind of collaboration with Porsche Institute in Switzerland, and what they did spallation they used spallation targets, protons. They used, which is in general it's proton beam, which hitting some kind of solid, some kind of matter, does matter, solid or liquid, and neutron. And since this beam is very high, this beam is produced by high energy accelerator, and the energies of protons are very high, and as a result, with small particles, neutrons coming out, and then those neutrons, which are called spallation neutrons, can be used for different things. Let's say for material science, for neutron tomography, cancer therapy, and so on. Their usual target type was solid target, which was composed on a number of rods filled with lead and cooled by water, which flows around them. And the proton beam is coming here on downstairs, where you see those arrows. So and neutrons are coming circularly outside, and scare some channels, and then they are taken from those channels. Specimens are put specimens close to this that target, and that target is very safe, but not 100%. Sometimes some bad things happens, like you see here. Then those rods are some cracks appears on those rods. They are opening. The lead it's molten because it's very high temperatures inside. It goes out and makes some and it's bad situation for safety. So they asked us to investigate numerically, and again we used OpenFOAM to analyze those structures. And also at that time, it was already up past 2010. There was some lot of work done even in stock OpenFOAM related to liquid-solid interaction. So we did some modeling of liquid-solid interactions related to those growths. And these models, here are some models, and this model is more work on that is done by Sabīne. She will present you, will do some OpenFOAM demonstrations later on during her PhD thesis. And also in PSI, they built some kind of experimental system, which you see here, and we did some validation. And finally, it went well. Sabīne got her doctoral degree. So that was the result. More recent things. Some multi-physics simulations, which I'm doing right now. I am implementing some dynamical extensions to OpenFOAM at the moment. And this is related mainly on my work in Latvia University, the Institute of Physics. We are doing some kind of pumping systems, let's say basically pumps, for liquid metals. Let's say lithium, sodium. Lithium pumps can be used, for example, for production of batteries for your laptops and so on. In those factories, they use lithium pumps. Also, some of those pumps are used in so-called different branch of research and engineering for aero fusion project, which is so some of them are also just packed and given by aero fusion project. And the pump works like that. And we have magnets here, which are connected to rotor. They are rotating, and those magnets are surrounded by pipe, which has a channel which has omega shape. And then that channel, some electrical field goes, magnetical field induces electrical eddy currents, and electrical eddy currents interacts with that magnetical field, and finally we get some volumetrical force, and this volumetrical force be giving a pumping effect. So that is also something which is, we looked at on console, we looked at on ANSYS, and all those models wasn't really what we wanted to get for the system. There was some problems with harmonics or and so on. So I just implemented it as C++ inside the additional library added to OpenFOAM, and finally, and with that small trick, that small library, I was able to simulate those pumps. I can do that, and that accuracy is more or less acceptable. You see, this is here. You see the productions. Let's say 63 liters per second. So that is typical. Speeds, velocities, pretty much actually. And here is some kind of 2.96 is experimental result, and 2.86 is calculated. So they are pretty close anyway. And the difference can be explained because the pump is sectioned by mechanical aspects and some more additional tuning, additional code is needed in the model in order to get those currents flow through the sections. Because at the moment our model assumes those sections insulated, which is not reality. And finally, last one is something totally different. I think Monty Python had this without wording somehow. something totally different, yes. And this is related to OpenFOAM calculations, which are used in medicine, in pharmacy science, and we are modeling it right now in some project drug delivery systems. We are modeling how tablets of paracetamol, for example, how it dissolves during the time when there's some kind of flow is around it. And yes, also again, we are using extensively rotating coordinate systems and different turbulence models, large eddy simulations, time. This is not stationary, it's dynamical models. And when we are looking on results, then you can see those curves, which I think is pretty good. We can see this guy's different rotational speed for this pendulum, which you see for such a kind of machine which is mixing water, and the bottom here is tablet. And during this mixation, the tablet is dissolving. And the dissolution speed by this rotational speed, you see there those curves here, and you see that our prediction it's kind of we cannot measure it because it is we can measure just average. Therefore, experiment is straight line, and prediction is something which you see this due turbulence phenomenon. It's stochastic. It's not really constant, and it's pretty much in average fits the expectations. So this we do together with Riga University. So those are major, so few examples. I am not demonstrating here some kind of body, full over body, well, let's say, of our because I have such simulations, but those bodies usually are some kind of unmanned airplanes or something like that, which I cannot basically show to you. Sorry, it's not my choice. I cannot legally do it. But this can be done as well. So those are just for inspiration, few examples where OpenFOAM is successfully used, and it's for free. It's someone says we have to pay much, no, but not really, you have to learn it. And my final note is I would like to consider as viable alternative in some, not on all cases, but on some cases, the commercial solvers or package for both, even for both, for academic research and for more practical, even engineering, some kind of real world engineering. This software package can be used. The strength is that it's for free. We have excellent community support. Nowadays it's very simple to add new physics or more elaborate numerical models. It's easy to tailor this OpenFOAM for particular problems. And as I told at the beginning, it scales well with numerical. You can get rapidly results. You can scale to numerous cores and several nodes with those cores, KPC plus clusters, and you can do calculations of GPU. And it's for free. You don't have to pay for more CPUs, for example. The main drawbacks is then we have no advanced mesh generators. Post-processing is more or less organized well, but I would like to see better mesh generations for pre-processing. Somehow steep learning curve, and something which I didn't tell, it is constant change. Then those OpenFOAM as open software evolves. People coming for open software community, people going from open community, and they do change, and new versions are coming, and that is okay because things have to evolve. But unfortunately, no one almost are interested in keeping compatibility with previous versions. And it's not problem if you are just using stock solvers. But if you are doing your own code base, which in my case, I have a lot of code, then you are experiencing frustration maybe, and some problems with keeping up to date. New version can be incompatible with previous, and since it's incompatible with previous, nothing is works in new version. Okay, let's use this previous version, but for some time, after some time, this old version doesn't compile in modern Linux distribution, for example. And you are pressed to port all your code to the newer version, and sometimes it's like that. Then this interface is replaced by new interface, and then they find that the new interface is not good enough and replace it back to the old. And that is something which maybe is a bit more stable in commercial world. But otherwise, I would like to suggest sometimes to have a look on open source package as well. Thank you very much for attention.
Thanks a lot, and I would like to make the certificate of attendance and making the MarTe Technical Workshop. So thank you very much. And any questions to Normunds? Maybe some questions to auditory? No raised hands. No, I have. Yeah, so I actually have questions that you already answered on it. Your previous works of models like 2006, 2012, in this case, you are not able to just take it and run in newer software.
Well, I updated everything.
Yeah.
I am regularly updating all my libraries, and I am making my code compatible with some software drifts, so it works on all versions practically, but it's take a lot of work to keep it that way.
And one more question about compatibility with high-performance computing in GPU. I remember from previous time it was rather challenging to run it on clusters, but how it works now in your version?
This development version, which is extended version, yes, which is not really official version, but extended version, it has CUDA solvers inside. So the thing that you need proper compiler, and you can do the cards, NVIDIA, and then it will work. I am not really, I don't know how it's about AMD. This another branch, which is OpenFOAM, for example. That is something which I don't know.
So thanks, and so it's a good example of free software, not like a SolidWorks is costly around 12, 15,000 per license. So it's for just like a small enterprises. I think it's very complicated to pay with licenses, but OpenFOAM is in this case more affordable.
Yes, sometimes yes, but of course you have to count inside your work as well. But
yes.
Okay. Yes, that's but people coming and asking to move some. Yes. Okay. Thank you very much.
Thank you, and we continue OpenFOAM topic. And next speaker Sabīne Upnere.